People are familiar with the TCP/IP protocol stack? Okay, then we won't have to spend too much time on it, right? This is the networking protocol that's in use on the internet, but it's also the protocol in use on most corporate networks now, right? It's really taken over from the proprietary network protocols. It used to be used by HP, IBM, DEC, etc. The original internet protocol wasn't named, but it had various components to it, like the host-to-host protocol, the front-end protocol to host protocol, etc. Today, the actual name of this protocol is called the IP protocol, and specifically IP version 4. There is an IP version 6, and it is run on parts of the internet. It's run over the internet. It's tunneled through the internet, etc. And there are some countries where they've widely implemented IP version 6, Japan and China, for example. And in fact, much of the Pacific Rim is far ahead of us in terms of IP version 6, just like they are in terms of energy efficiency and being green, etc. So the US government, and specifically the DoD, in many cases, after they got over trying to mandate the OSI protocol and gossip, then they began to start mandating IP version 6. And not all parts of the government have fully implemented IP version 6 yet. There's a variety of different reasons for implementing it. The main one, the reason for which IP version 6 was actually created was what? So it was IP address exhaustion. We managed to stave that off throughout the 90s and the 2000s, but we're running rapidly toward IP address exhaustion. IP addresses, public IP addresses are a scarce resource, and people pay good money for them. They want them because we don't have that many. But we did manage to stave it off through things like network address translation, NAT, and using proxies in firewalls, etc. That's gotten us so far. We actually have people that are running NAT devices with NAT devices behind them and all kinds of cascading NAT. And that causes problems. It causes delays and propagation problems, etc. But the other reason that IP version 6 was created, although it wasn't really the primary reason, it's really the reason why we need to go to IP version 6 is security. IP version 6 builds security in at the network protocol layer, right at each layer in the stack. We can get some of that with IP version 4, but IP version 4 was not designed for security. It was a research experiment, right? It was written by some guys at universities. They were on these DARPA contracts, Defense Advanced Research Projects Administration. Back in 1969, they created the ARPANET just to see if they could link computers together. They played around with that for almost a decade before they implemented TCP/IP. But TCP/IP itself was trusting. There's no cryptography in there, right? There's no real security in TCP/IP at all. Any security that's in there had to be added on later and tacked on and hammered on. And so people did create security. In some cases, they put cryptography, but it wasn't a part of the basic protocol, right? So where they've inserted VPNs or where they've inserted encryption in the data link network, or even up in the transport of the session layer protocols, or even at the application layer protocol, because SSH is actually an application layer protocol, right? A secure application layer protocol. Another one, which is closely related to it in terms of its naming, although not in how it actually functions, is what? SSL. Has nothing to do with SSH, but it's another application layer protocol. And in fact, usually people will argue with you and tell you that it's a session layer protocol. Really, it's meant to be run at layer 5 and 6 or so. So we'll look at the transport layer. We'll talk about what security may or may not exist at each layer, but we'll do it relatively quickly, right? TCP/IP was designed before the OSI model, which was developed by ISO. You just reverse the order of the letters. OSI is Open Software Interconnect. It was developed by a group called the International Standards Organization, which is a lot of international postal, telegraph, and telephone union people in many countries, right? So they got together. They had these big committees. They over-designed lots of protocols, as government and other monopolies and bureaucracies will do. And the result was that it was too large to implement. The whole standard and the spec was way beyond what most people wanted. As a result, people fell back on TCP/IP, even the military, even the US government. TCP/IP was much more widely implemented than the OSI protocols out there. But some parts of the OSI protocols were implemented, and some parts are still with us today. X.25 was an OSI protocol. X.500, which is used in LDAP. LDAP is a lightweight version of the X500 directory service. So anything that starts with X dot, that's usually a ISO protocol or an OSI protocol. You'll also see some other ones that were developed by other groups like the CCITT, etc. So any of the H dot protocols, which are used for video and audio, You know, the codecs for video like H.323 and 263, etc. Those are other international standards. TCP/IP, because it predates the 7-layer model, it really only has 4 layers, right? And they look like this. Everything below TCP, TCP is built into the kernel. It's not running in user land for the most part. What's in user land? Your applications. Now, if your application really does have a session and a presentation layer, they're also inside the application layer. So here you've got your application layer, and then you've got your presentation layer just below that. There's mnemonics to remember these names. This is presentation. And then we've got the session layer. So the session layer would be used, for example, if you're running some encrypting protocol right on top of your TCP/IP sockets. SSL is one. It really stands for Secure Socket Layer. Right. Then in the kernel, you've got your other pieces of the protocol stack. So they're implemented inside this secure code here. This stuff you can muck around with in your program if you want to. Now, usually the presentation or session would be in shared libraries, which are separate from your executable, right? Your application really only contains your application code. In the application code, that would be your application protocol. So if you write your own protocol, it could be byte-oriented or record-oriented or whatever. That's your application, and you design what you want acknowledgments to look like. You design what you want your queries and responses to look like, etc. Or you can use somebody else's application layer protocol. Like HTTP is an application layer protocol. There's other ones like SMTP, you know, FTP. Notice a pattern here. And most of those are all text-oriented protocols. They send over these things called verbs, and they get back these numeric strings. But they're not really numeric. They're actually printing out the value of the numeric digits or as characters. That's a pretty common one that you find in TCP/IP in the internet. But there are binary protocols, record-oriented protocols, bit-oriented protocols. Down here in the kernel, this is where we see at first the network layer. No, sorry. Transport is first, then network. Transport layer protocols are TCP, UDP, and there's some others, including ICMP, which actually exists at both the transport and the network layer. Then we have the network layer. The network layer protocol is actually IP. IP, Internet Protocol, is the layer 3 protocol. And then in layer 2 is implemented in this device driver, right? So if this is an Ethernet device driver, I'll put Ethernet here. At layer 2, we've actually got either the old classic Ethernet, which some people call DIX or DIX2, or we've got the newer, fancier IEEE Ethernet, which is called 802.3. And Wi-Fi is 802.11. It comes in a bunch of little flavors depending on your speeds and feeds and your frequencies that you use, right? Whether it's A, B, G, N, etc. So here's where you've got your 802 protocols, 802.3, 802.11. And Ethernet and wireless are different. They have packet formats that are similar, but they're not exactly the same. Classic Ethernet is much more different because it's missing a lot of the fields that IEEE packets have. Right? And then below the data link layer exists what? The physical layer. And that's where you've got your wires, or you've got your radio frequencies, and then you've got your power levels for those signals, what the different electrical voltages are, what the shape of those signals are, you know, how do you construct a bit from a waveform, etc.